Good morning. Can you hear me okay? Okay, wonderful. Hope everyone's having a great reInvent so far. Welcome to CMP322. This is our session on where we're going to deep dive into our new Graviton 2 CPUs that we announced yesterday, as well as our new EC2 instances that are powered by these CPUs. I'm Sudhir Raman. I'm a product manager in EC2. And co-presenting with me today are Ali Saidi, principal engineer at AWS. And we also have a guest speaker today, Sudhir Kakula from Nielsen. Thank you for joining. So what we have for you in the next 45 minutes or so is, here's what we have on deck. We're going to do a quick recap of the first generation Graviton CPU that we announced last year at reInvent, and the A1 instances that are powered by the first gen CPU. We're going to talk to you about what's happened since in terms of customer momentum, success stories on customers that have been able to adopt and run their workloads on Graviton instances. We're also going to give you an update on the growth in the Arm software ecosystem. And then we will deeper dive into our Graviton 2 CPUs and the new instances. And finally, we'll have Nielsen coming on stage and telling us about their Graviton journey. So as we take a step back, our goal is to be able to support every workload that runs in the cloud. And to that end, we've been innovating across instance types, pretty much across our entire instance portfolio, be it our general purpose instances, our compute storage or memory optimized families, or our accelerated computing families. We've also invested in a number of capabilities over the last couple of years. That includes working with Intel to get some of the faster processors, or collaboration with NVIDIA on some of the GPU capabilities, or introducing instance types that have higher networking that support up to 100 gigabits per second. And all of these also come with options where you can attach elastic block store, elastic inference, elastic graphics across our different instance types. So as all of this comes together, we have more than 270 instance types today that can meet the needs of every single business workload. What we also offer is a choice of processors within our instance families. So we've had a rich and a long-term collaboration with partnership with Intel. And the Xeon scalable processors have been key to powering many of our instance types, including some of our most recently announced C5 larger instances, our M5, R5 higher networking instance types, our storage or our high memory instance types as well. And last year, we also announced that we have instance types with powered by AMD CPUs, mainly their EPYC processor line. Today, we have the the M5, the R5, and the T3 instance families that are powered by AMD CPUs. And we've also signaled our commitment to use the next generation of AMD Rome CPUs with our C instance families. And finally, at reInvent last year, we also announced that AWS is building its own CPU, the Graviton processor. So as most of you may know, the Graviton CPU, the first gen that we launched last year, was built utilizing 64-bit Omniverse cores and custom silicon that is designed by AWS. And by building our own silicon based on our knowledge of running hyperscale workloads and our knowledge of operating cloud infrastructure, we are able to build in targeted performance and cost optimizations for cloud-native workloads. And also, this allows us to build, iterate, and innovate continuously based on customer feedback. So the first instance that was powered by the Graviton CPU is the A1 instance that, again, we announced that last year at reInvent. And we specifically targeted the A1 for scale-out workloads that are more I/O bound. And for those workloads, the A1 instance delivers significant cost savings. So this includes applications such as web tier, containerized microservices, essentially applications that can be distributed across multiple smaller cores and fit within a certain available memory footprint. What we've also seen is a lot of the ISVs, software developers, have been using the A1 instances for Arm development natively on Arm hardware in the cloud, as opposed to either procuring real devices or cross-compilation or emulation. And in terms of configurations, we support 6 instance sizes, up to 16 vCPUs, with both enhanced networking as well as EBS support. And since we've announced the A1 instances and introduced them, we've also been working to enhance both the capabilities as well as the global availability of these instance types. For example, we introduced most recently a bare metal version of the A1 instance, targeted at applications that may need access to the underlying server resources such as the processor or the memory. So that makes it ideal to run non-virtualized workloads or workloads in a non-virtualized environment on bare metal instance types. And in terms of global availability, the A1 availability has now grown to 9 regions. That includes 3 in the US, 4 in APAC, and 2 in EU. And all of these instances are, by the way, built on the AWS Nitro system, which allows us to offload storage and networking from the host processor and deliver maximized resource efficiency back to the instance. And it also allows us to innovate faster and deliver cloud services at scale securely. So in terms of customer success stories, what have we seen in the marketplace since we introduced the A1 instance? What we've seen is that thousands of customers have been able to transition a lot of their workloads, such as scale-out workloads, built on Linux, open source software, languages such as Java or Node or Python or PHP that are generally architecture agnostic and can easily run well across multiple processor architectures. And those have been the fastest to transition to A1 and have realized cost savings. And we've also seen, essentially the developer ecosystem pick up these instances for native development on Arm hardware. So here are some specific examples that I wanted to cover today. First up here is NetEase Games. And as many of you may know, NetEase is a leading internet technology company that operates and develops PC and mobile games. And one of their most popular games is the Knives Out, which happens to be a household name among gamers and especially in the Japan and APAC region. And today they are using the A1 instance for their network-bound applications. And since most of their code base was based on Python and Java, they were able to easily get that moving to A1 instance and have realized up to 40% cost savings. And specifically, the applications include their real-time player chat within the game, as well as some of their network forwarding service apps. And here's a quick look at their architecture for the Knives Out game. And the boxes that you see marked out in pink are currently the ones that are running on the A1 instance types. And what we're showing here is their Tokyo cluster as an example. So you can see the web proxy as well as the web chat interface as part of their network acceleration infrastructure. And a few more examples that we can cover today. SmugMug, as most of you know, is a safe, beautiful home for your photographs. And SmugMug has transitioned their photo serving tier onto the A1 instance. And their application stack consists of Ubuntu as well as PHP, Nginx, and HA proxy. And they pretty much had a very seamless transition onto A1 and have been able to realize 40% cost savings. Another example here is Reamp, a company that's based out of Brazil that helps their customers develop better marketing insights. And for their data processing workloads, which again is a very good scale-out workload example, they were able to get their OpenJDK application to A1 and save 20%. DigiIntelligentsia is another example, company based out of Mexico, an IT company. They use their web traffic on A1, so that's Nginx, .NET Core, as well as Docker. All of these are extremely well supported on the 64-bit ARM architecture, and that delivered cost savings for them. And finally, I have an example here of an ISV, Rancher Labs. As Rancher was developing K3s, which is a Kubernetes for the edge on ARM deployment, they needed to run their CI infrastructure on ARM servers. And to avoid the pitfalls of emulation or cross-compilation, often that can be error-prone or might result in delays, they instead resorted to building and testing directly on A1 on ARM hardware in the cloud and take advantage of the elastic nature of the hardware that we provide within the cloud. So along with the customer momentum, what we've also seen is a strong growth in the Arm software ecosystem and for Graviton instances. So when we look at the operating system vendor space and the independent software vendor space, we see that most of the popular Linux distributions today support 64-bit Arm architecture. And these include Amazon Linux 2, Ubuntu, Red Hat Enterprise Linux, SUSE Enterprise Linux, Fedora, Debian, FreeBSD, and many more. And we've also seen on the EDA space, the key ISVs such as Mentor and Cadence, they have their EDA tool suite supported on 64-bit Arm as well. And VMware has successfully been able to integrate and run their ESXi on A1 bare metal and have also now support the 64-bit Arm and Graviton instances. And finally, with our support in AWS Marketplace, we have a lot of ISVs that have been able to release their packages into our marketplace, such as Nginx Plus. There's an AMI available today that allows customers to be able to deploy their web server or their load balancer easily on Graviton. I guess we're getting some special effects, so we'll keep that going. On the container space, so most recently at DockerCon earlier this year, Docker announced support for 64-bit Arm within their Docker desktop as well as Docker Enterprise Engine. So that now allows thousands of developers to be able to build and deploy multi-arch images. And the Amazon services that deliver for containers, such as the ECS and the EKS services, also support the Graviton instances today. And finally, we have support from Firecracker that allows you to deploy micro VMs. In terms of developer tools and developer software, all the popular agents that our customers rely on within EC2 for security or monitoring, such as CloudWatch, Amazon Inspector, or Systems Manager, they are fully supported on Graviton as well. So from a customer perspective, it would look like just like any other EC2 instance. It's a consistent experience. And we also support the entire AWS code suite. So that includes code build, code pipeline, code deploy, code commit, as well as Cloud9. And most recently, we also announced support for Amazon Corretto, which is a no-cost distribution of OpenJDK that provides an additional Java runtime option for customers to be able to deploy Java applications. And that's not everything. So we also now have Datadog that has announced a GA support for their agent on Graviton and Arm. So a lot of our customers do use Datadog, as you know, is a very popular monitoring and analytics platform. And that agent is now pretty much available on Graviton and Arm and gives you a consistent experience across EC2. Another ISV that's adding support for Graviton is CrowdStrike. They deliver cloud-native protection. And as they see increased demand for ARM64, CrowdStrike has now also added support for the Graviton instances. So if you can learn more, they have a booth over here, and as well as an email. If you're interested in CrowdStrike support, you can reach out to them. And in terms of our workload optimization journey, for us, this has been more than 5+ years of innovation with Annapurna Labs building custom silicon solutions. And the Graviton, the first generation, was simply a start in that journey for us. And as more customers adopt A1 and have realized significant cost savings, and based on that positive experience, they want to be able to run more demanding workloads on Graviton-based instances. And that could mean applications such as compute-intensive data analytics or memory-intensive databases. And a lot of these applications typically require enhanced capabilities than what we first delivered with our A1 instance, such as more compute power per vCPU, or higher memory per vCPU, or enhanced I/O capabilities with higher networking, higher EBS performance, or the ability to be able to scale up to larger instance sizes. And as all of this comes together, and as we look to broaden the number of workloads that can take advantage of Graviton instances, we are super thrilled and excited to be able to innovate on our Graviton line and talk to you about the Graviton 2 processor that we announced yesterday. So how many of you caught that announcement? Okay, that's awesome. So the Graviton 2 processor is a significant leap in terms of both performance and capabilities that we deliver over the first generation. So compared to the first-gen Graviton processor, the Graviton 2 CPUs offer 4x the number of compute cores, 5x faster memory, and that results in a net 7x performance improvement over the first-generation CPU. And we've also announced 6 new instance types that are going to be powered by the Graviton 2 CPUs. And these are now part of our general purpose, compute optimized, as well as memory optimized instance families. And as you can see, they are our first 6th generation Amazon EC2 instances. So our M6G, C6G, as well as R6G instance types are going to be powered by Graviton 2 CPUs. And they give you more options in terms of the DRAM per vCPU that's supported, or both in terms of enhanced networking and I/O capabilities. The M6G instance is available in preview, so if you're interested, you can sign up for it. And in terms of the availability, we'll have all the other instances coming soon in the next few months. We also support these instance types with local NVMe instance storage. So there is the M6GD, the C6GD, and the R6GD versions that offer NVMe local instance storage support with these instance types as well. So with that, I would like to request Ali to come on stage and deeper dive into the Graviton 2 CPU.
Thanks, Sudhir. So in the next few slides, I'm going to talk about some of the technical details of the processor, and then I'll talk a bit about the performance we're seeing with it. So the first Graviton processor we announced last year, it was the first ARM processor in AWS. It was the first ARM processor in a major cloud vendor. And we really proved it was a first-class citizen in EC2. But from a technology point of view, it was a 16-nanometer chip. It was about 5 billion transistors. It wasn't earth-shattering. With the Graviton 2, we have, as Sudhir mentioned, 4 times the number of CPUs, over 7x the performance in the chip. That turns out to be about 2 times the performance for every vCPU from the A1 instance, which is a big leap. And it's built in an industry-leading 7-nanometer process. It has around 30 billion transistors in it. The pictures you see here are to scale. You can see how much bigger the Graviton 2 processor is. On the back of it, there's over 4,000 pins. I've got one in my pocket here. And in the next few slides, I'm going to lift the lid on this and tell you about what's inside. So let me start with the cores. We use ARM Neoverse N1 cores in the Graviton 2 processor. They're ARM v8.2 compliant. And we work closely with ARM, bringing our expertise as the world's largest cloud vendor, along with their expertise in microarchitecture, to define a feature set of the CPU that we think is really amazing for cloud workloads. We use large L1 instruction data caches of 64 kilobytes and a large private L2 cache of 1 megabyte for every vCPU. This is twice the amount of cache we had on the A1 instance and twice what we see in an M5 instance, for example. And it really means that you can fit your large percentages of your workload in that cache, which means they don't have to go to memory and they just run faster. We have a coherent instruction cache. When we built the first Graviton 2 chip, we found some places where not having a coherent instruction cache was a problem, so we had that feature added. And really, the microarchitecture in N1 focuses on reducing the overheads of interrupts, of virtualization, of context switching, because it's very different from the way a mobile application runs. When a server application will see tens of thousands of interrupts per second, it might see tens of thousands of system calls a second. And so those overheads to go from user space into kernel space have to be really cheap. And they are in this processor. From the actual technical details, it's got a 4-wide front end, so it can fetch and decode 4 instructions at a time, and it can issue 8 in the back end. It's got twice the number of SIMD units as our first Graviton processor, and those SIMD units have specific instructions to accelerate IN8 and FP16 that's used for machine learning. And every vCPU here is a physical core. There's no SMT. That means there's more isolation between vCPUs. It means they don't share resources except in the last level cache in the memory system. So every vCPU has similar performance characteristics. And it also lets us offer smaller instance sizes. So with M6G, we're offering a medium instance, which is smaller than any current generation M. So we took 64 of these cores, and we put them together with a mesh. And the mesh provides almost 2 terabytes a second of bisection bandwidth, which means when your application shares data, it can move very quickly from core to core. The picture you see here on the right is the picture of the actual die. It's a monolithic die. There are not any chiplets. There are not any NUMA regions. Every core sees about the same latency to every other core and about the same latency to DRAM, which means you don't have to worry about where you're going to finitize a CPU on what cores or where the memory is coming from on those cores. It's all about the same within a few nanoseconds of each other. We have a 32 megabyte last level cache here. So if we take that last level cache plus the 64 private 1 megabyte caches and the L1 caches, there's over 100 megabytes of cache that's user accessible on this processor. I mentioned there are no NUMA concerns. Every core sees the same path to memory. And then we have 64 lanes of PCI Gen 4, which provides flexibility for different instance configurations, some of which Sudhir shared with the ones with instance store and without. At the system level, we have 8 DDR4 3200 controllers. That's over 200 gigabytes a second of theoretical bandwidth. Every DRAM controller generates a key at boot, an AES key. All the traffic to the DRAM is encrypted, and when the server is shut down or rebooted, those keys go away and are not retrievable. I mentioned the uniform latency. In addition, the cores of the memory system work well together, and so it's really easy to extract that bandwidth. You don't need a special program. You don't need special instructions. Just simple loops can get you a lot of the way to the 200 gigabytes a second. And lastly, we have over a terabit a second of compression accelerators. So the larger instances in M6G will have a compression device. We're going to open source DPDK and Linux drivers ahead of GA. And you can compress data at 15 gigabytes a second or decompress it at 11 gigabytes a second. So in really low latency, you can take a chunk of data, compress it, store it in RAM maybe, and get it out of there when you actually need it. So with this, we have 4 purpose-built modular building blocks built exclusively for AWS. The Graviton 2 CPUs, which in a couple slides I'm going to show you have industry-leading performance. The Nitro security chips, so there's one of these integrated on every one of their motherboards. It protects the hardware resources. It makes sure that NVRAMs and similar have not been tampered with. Our Nitro cards, these offload things like elastic block storage, elastic networking adapter, provide monitoring and security for the instance, and move a lot of the functionality that people typically have in a hypervisor onto dedicated special purpose hardware, leaving more of the CPU for your applications. And that's coupled with a Nitro hypervisor. So this is a very lightweight hypervisor. It does memory and CPU allocation and provides bare metal-like performance. And with these, we can really broaden the workloads that are applicable to our Graviton-based systems. When we launched A1 last year, we focused on web tier and caching hosts and containerized microservices and dev and test. And the 6 new instances are good for that, but they also have advantages across nearly everything that we've tried. That's from web servers to high-performance computing. Whenever we've done FP-intensive apps, we've been impressed with the performance. Media encoding, I'll share some numbers with you in a few minutes. Analytics, same for open source databases. I'll share a few examples there, and in-memory caches. EDA tools, these are tools that we use to develop the chip itself. We've been running some of those, and some of our partners have. We're seeing impressive performance there, and finally microservices. So we have 8 virtualized instances in the M6G family, starting with an M6G medium. It's got 1 vCPU and 4 gigabytes of RAM, all the way up to an M6G 16X large, which has 64 vCPUs, a quarter terabyte of RAM. Now, there are a couple things here. All these are priced 20% cheaper than the corresponding M5 sizes. The M6G medium, we can't offer a medium on the M5, so that instance is actually 40% cheaper than the smallest M5 you can get. And the larger instance sizes here have more EBS and more networking bandwidth than their M5 counterparts. So we've talked about the chip. Now I'm going to spend a few slides talking about some of the performance we've seen and comparing that to our M5 instance. In all these cases, these are real servers in our real data centers alongside their M5 counterparts. Where it's applicable, they're in a placement group with other servers. And so let's dive into some of those numbers. It seems like no CPU would be launched without talking about spec CPU performance. And 2017's been out for a few years, so we're focusing on that. For those of you who don't know, these are CPU-intensive workloads. They do things like, it could be Perl, compiling code, route planning, XML processing, Sudoku solvers on the integer side. On the FP side, things like physics or ray tracing, weather forecasting. They're all written in a combination of either C, C++, or Fortran. And for these, we're running what's called spec CPU rates. We're running 1 copy of these for every vCPU in the system. On the y-axis, we've got performance versus M5. M5's in yellow, and M6G is in green, and that trend will continue for the next few slides. And you can see here that on the integer side, the M6G is about 44% faster than an M5, and on the FP side, it's about 24% faster. Now, there's a lot of Java in the world. We run a lot of Java internally. We wanted to get some idea of how does it perform on a Java workloads. So we looked at Spec JVM 2008. These are micro benchmarks that do everything from cryptography to serialization and XML processing. And similarly, you can see here the M6G is performing about 42% better than an M5 on these workloads per vCPU. Now, transitioning to something that's similar to what our customers typically run. Nginx is a popular web server. It can also be configured as a load balancer. And so here we've got a load generator. This is a C59XL. And it generates, it's simulating load of clients. It's simulating 512 clients, making a request to a load balancer. That load balancer could be an M5 or an M6G. They're both 4x larges here. And then we've got 4 web servers. The web servers are running Node.js. They're also 4x larges. All these are launched in a cluster placement group. And we're measuring the number of requests per second that load balancer can pass. So the load generator makes a request, sends it to the load balancer. The load balancer picks one of the web servers, sends the request there, waits for the response, and passes it back to the load generator. And for all these, we're using relatively small gets and puts and gets, all encrypted with HTTPS. And you can see here the M6G is getting 24% more throughput than the M5. Similarly, with a key value store, with Memcached, people use key value stores to quickly look up data faster than they could in a database. Databases typically measure transaction times in tens of milliseconds or even seconds, while key value stores tend to measure responses in microseconds, tens of microseconds, hundreds of microseconds. And so here, too, we've got 3 load generators. They're all C59XLs, and we're either running against an M5 or an M6G. There are 2 XLs here. And we have 2 load generators that are trying to generate as much load as they can, and a 3rd load generator that's really just focused on a few connections where it can measure latency. Because, as I mentioned, latency is really important for this workload. So from a throughput point of view, if we just throw as many requests per second at the instance as we can, we see that we're seeing 43% more requests per second with the M6G. And then if we look at the latency graph, so the optimal here is as far to the right and low as possible, we can see the M6G maintains a lower latency than the M5, and also, depending on where you are on the curve, substantially more requests per second. Now, there's a huge amount of video that's created every day, and to reduce the storage and transmission costs, we encode it. So one we asked ourselves, well, how does this perform on media encoding? We took uncompressed 1080p video, encoded it with libx264 with a medium preset to see how well does this perform. And in doing so, we see that we get 26% more performance than the corresponding M5 size. And machine learning. Our machine learning team has been looking at, has been playing with these instances. And one of the things that is critical for ML is feature representation. So BERT is a state-of-the-art text encoder. And I mentioned several slides ago, we have specific instructions to accelerate ML, FP16 and int8. And even though the M5 has AVX512, so they have a lot larger SIMD vector width than we do in an M6G. With the FP16 support in M6G, we can see inferences at 28% lower latency with a batch size of 1. So this isn't a throughput exercise. This is sending one inference. How long does it take me to get that one result back? We also made one of these instances available to Arm. And in the process of building Graviton 2, we did a huge number of simulations of the chip before we built it. But that was actually small to the number that Arm does every month to simulate the processors and IP they develop. And the reason that we spend so many resources doing simulation ahead of building a chip is that as a software developer, our build, test, and debug lifecycle is measured in minutes, typically. We can build something, we can test it, we can see the results, and we can try again. In the silicon world, it's measured in months. And so you have to get it right the first time. If you have a mistake, it's going to cost you months and all the money associated with that. So every month, Arm uses millions of CPU hours to simulate their designs. But that demand is highly variable, depending on the phases of their various projects. And this is a perfect use case for Amazon EC2, where as demand increases, they can launch more instances. And as demand wanes, they can stop those instances. So when we made this M6G available to Arm, that was one of the first things they're interested in. How does it perform on their business-critical workloads? So they took 570 real validation jobs that they run on a Cortex data path, and a Cortex core, and ran them on an M5 and on an M6G with Cadence Xcelium. And you can see here that the runtime was a little over 6 hours, 6.5 hours, and the M6G is about 2% slower. But unless you're looking carefully here, the M524X large has 33% more cores than the M6G. So per vCPU, we're actually getting 50% more performance on this workload than the M5. So what about a database workload? We gave one of these to Scylla and asked them, what do you think of this? For those of you who don't know, Scylla is a high throughput, low latency, big data database. They've really built their code to be able to take advantage of all the CPU resources and all the storage resources in any system. And when we gave it to them, they said, yeah, we've run it on an A1. That's nice. It works, but it doesn't, on an A1, it doesn't perform like we think it needs to be really successful. And in their words, M6G changed the game. When they started running on the M6G, they found 5 times more performance than they were getting on A1. That's almost 38K reads per second per CPU. Or at 64 vCPUs, about 2.4 million reads per second they were getting out of memory. But from a storage point of view, they were still limited by the IOPS they could get on EBS. So we let them use an M6GD, one with instant storage, for a little bit. And they found they could get over 5 gigabytes a second of disk bandwidth. They could extract nearly 1 million IOPS. And again, in their words, they welcome the M6G series. It's ready for NoSQL. So with this, we have instances that are some of the highest performing in their instance families. They're 20% lower cost than an M5, and up to 40% better price performance than those comparable instances. Now, since we launched A1, various teams inside of AWS have started making their code multi-architecture. And the Amazon Elasticache and Amazon EMR team are going to be offering M6G instances as options in the coming months. And the Elastic Load Balancing Service is going to be transitioning to Graviton 2-based powered load balancers as well. Beyond this, there's going to be a lot more coming soon. So within 2 months of announcing A1, Nielsen was already running production workloads on it. And I want to welcome Sudhir from Nielsen to tell you about their experience with A1 and how they found the M6G instance as well. Welcome, Sudhir.
Thanks, Ali. My name is Sudhir. I'm a vice president at Nielsen Digital. Good to be here with you all. Very excited to be here. Great sessions. So today we will cover what do we do at Nielsen, the migration of our digital collections platform to AWS and what we learned from it, and then the ROI problem that we soon ran into, how the Graviton processor helped us solve the ROI problem on our end, and what's our future in AWS. Let's get started. So most people, how many here know about Nielsen? Well, most people know us for our TV ratings. We have a strong presence in the TV ratings world. We've been in the measurement business for over 90 years now. Media around the globe is traded based on the Nielsen's ratings data. And we are the independent third-party measurement company that publishers, broadcasters, and advertisers trust when making their media decisions. The focus of my team, however, is outside the TV world. Our focus is digital measurement. We provide insights on how people consume media outside the traditional TV world. We provide measurement across screens such as mobile, tablets, cell phones, and desktop. And we also provide insights as to how people interact with their media, like how long they watch content and for how many times. And we also provide insights into how people are buying media in the digital age. The problems we solve in digital are very different from the TV world. We deal with highly dynamic data sets that grow and shrink very fast. In front of you is a figure that shows the comprehensive view we can provide to our customer. It's data that shows how many people watch an episode of a drama that was initially aired on a cable, and within 30 days, how many people actually watch it from a computer, from a mobile, and how many actually watch the same episode over a streaming platform. So it's an interesting tale. So that brings us to the next section we have, is that we want to discuss our collections platform migration. The work we do in AWS is incredibly important in how we deliver products to our market. Today, we are going to discuss the collections platform. It's a Java-based application. It collects over 10 billion requests globally on a normal day. It generates around 2.5 terabytes of data every day. It's a currency-critical platform. That is, people around the world, when they're buying and selling media, the data from collections matter. So it's very critical for our business. It runs 24/7 and has zero downtime. So why did we choose to move it to AWS? Well, we deal with dynamic loads, as I mentioned earlier. During NFL, the traffic can go from anywhere between 60 to 120% in a matter of minutes. So we always need to have the needed number of servers running to process that dynamic load. So AWS was the obvious answer for that. We wanted to have a controlled blast radius. So if there are issues in one region, we didn't want those issues to cascade to other regions. If we had issue in one account, we didn't want it to cascade it to other accounts. So that was another reason why we wanted to move to AWS. And we wanted auto recovery and self-healing. So if one server turns unhealthy, we want that server out of our production environment and replaced with a brand new server. So auto-healing was critical to us, and we wanted to support fast product launches across the globe. How did we do it? It took us roughly 2 months to do it, and that's also possible because AWS provides great documentation. It was easy for our engineers to understand and adapt our strategy, and we did it doing a fully automated blue-green deployments. And for folks who are not aware, who don't know what blue-green deployment is, in production, we always have a set of servers that are processing traffic. So when we want to do a release, we bring a brand new set of servers, and we transfer the traffic over to the new servers and get rid of the old servers. It was something that we could never do in on-prem. It's just way too difficult. On cloud, we could do it. And we also use a combination of reserved instances as well as dynamic scaling. So reserved instances provide us cost efficiency when the traffic is normal, and on-demand instances help us scale when the traffic suddenly grows up. We also support immutable deployments in our release process. So once the release is done, engineers don't need access to production systems in order to address issues. It's just taken care by auto-scaling and auto-healing. The results of our migration is, in the last 1.5 years, we've had rock-solid performance and reliability. And using a combination of SQS and S3, we were able to reduce our latency from 120 milliseconds to 20 milliseconds. We can do new region rollouts in less than 2 hours. It was something that used to take months. We had to negotiate contracts with data centers, and then we could do a rollout. But with AWS in picture, we can do it in 2 hours. And we have a lot more agility in how we support our business initiatives. So this is how our architecture now looks after migrating to AWS. On the left side, you see all these devices that are sending data: mobile devices, desktops, tablets, even gaming consoles, Amazon Fire Stick, and OTT devices. We call them over-the-top devices like Roku and Fire Stick, and smart TVs. So they push their data, it comes to the cloud, comes to our ALBs, and we also use in our application architecture Route 53 for DNS management. We use Lambda expressions for dynamic scaling to decide how many servers should be there in the production. We use SQS for offline message processing, S3 and Glacier for storage and archival, and quite recently, we moved even our build pipelines to Amazon Code Build. Everything was going great till we ran into our first problem, the ROI problem. We soon realized that our M5 fleets were not fully utilized. So we had chosen M5 based on our on-prem experience. It's a great server. It was rock solid. But it was just too much of a server for our application. And we were not utilizing all its potential. We were using less than 35% of CPU. We were using less than 57% of its memory. And it's not great. It's not good ROI. So we wanted to find a solution to improve our utilization. It was a very serious problem for us to solve. And while we were looking at technology solutions, such as looking at our architecture and other things, in 2018, we found out that A1 is born. We heard it was 46% cheaper than an M5. We found out that it's Arm-based, and it was ideal for scale-out architectures, applications that scale up very fast and shrink down when there is no need. So we wanted to give it a serious try. So in our 2-month dash, we had a couple of challenges ahead of us. There was a bit of work that we had to do in order to move to A1 from M5. Our very first challenge was our favorite monitoring tool, Datadog, was not available on A1. It was a year ago. Now they are available, so which is a great news. Right? So we ported Datadog to A1. The next challenge we ran into is A1 had just 16 gigs of RAM. So we made optimizations to our application to bring our memory consumption down to 13 gigs. That left 3 gigs for growth. And then we tested and tested and tested for weeks together. We made sure every optimization that we made was functionally correct and was performing well. And once these tests were done, we subjected A1 fleet to a dynamic load test where we would generate traffic that would spike up and come down, spike up and come down. And we did that for weeks together. And as the test results started pouring in, we kind of fell in love with A1 because it was beating every test we could throw at it. And finally, after all the test results were validated, we decided that we will adopt A1 in every region available. We work with Raman and Ali's team to coordinate our releases because a year back, they were still rolling out to different regions. So everywhere A1 became available, we just adopted A1 in that region. We are very happy with our decision. And some of the results of that decision are, in the last 8 months being in production with A1, we've again had a rock-solid performance. We are currently running in 4 regions. We have a fleet of 120 servers. On an average, again, the number of servers can go up and down based on the traffic volume. We use a combination of reserved instances and on-demand instances on A1. And we have achieved 60% CPU utilization in production, which is a significant improvement over M5. And we can run it hotter, we can achieve a higher utilization, but it's production, we keep certain amount of capacity just to deal with traffic spikes. And we have managed to achieve significant cost efficiency by switching to A1. So in short, by switching to A1, we solved our ROI problem. Here are some load test results in front of you we conducted back in 2018. On an M5 server, we were able to push 2,200 requests at a utilization of 30% of CPU and memory utilization of 56%. And the server took 20 milliseconds to process each and every request. And on an A1, we were able to push 1,800 requests using 70% of CPU and 80% of the memory. And the server, again, took just 20 milliseconds to process the request. Which brings us to more exciting news. Earlier this year, AWS reached out to us and asked us if we would want to test drive the M6G server, and we were very happy to run some benchmarks. And here are some other results. In our test, we found that M6G is twice as performant as A1. It was able to process twice the number of requests. On an A1, and you would notice that in 2019, our A1 version of our application actually processes even more requests. That's because we made a lot of optimizations in the last 1 year. So on A1 now, we can process 3,500 requests. On M6G, we can process 6,900 requests. On A1, we were using 70% of CPU, 80% of memory, whereas on M6G, we were using 64% of CPU and 56% of the memory. So we are really excited about the new processors. That brings us to the final part of my presentation, our journey in AWS. When we started our migration to cloud, AWS was just a vendor. They were a vendor, we were a client. And we loved their technology offerings. We loved their reliability. But in the last 2 years, and especially around the A1 effort, we've created a collaboration. And that vendor-client relationship has transformed into a partnership. Now, if you ask me, I would say that AWS is our partner in success. And I'm very confident that this partnership would only thrive and grow with time. Thank you for giving me the opportunity to share our story. Thank you. Back to you, Raman.
So that brings us to the end of our presentation. I just want to leave you with a few key takeaways. So in summary, the Graviton 2 processors offer a significant leap in terms of capabilities from the first gen. We've announced new instance types that offer up to 40% better price performance versus our current comparable instances. And the M6G instances are available in preview today. So if you go to the M6G webpage, there is a sign-up form, just a few simple questions that you can answer and put your request in. And it gets routed to us. We'll take a look at it and provide you access. So there's a link over there where you can learn more and also request access to the preview. So thank you very much for coming. And if you could leave your feedback on the mobile app, the session ID is CMP322. Thank you very much for your time.